let's just look at the chemical formula. So when we have, this is our sodium carbonate crystal, and when we have a dot XH2O, that just means the X, we don't know, it's a variable, so this could be a number, 5, 10, 12, 20, whatever it could be. And that means that for every molecule of sodium carbonate, there's going to be an X number of molecules of water attached to that, and it's hydrated, like water, hydration. That's why we call it hydrated sodium carbonate. So we're trying to figure out how many molecules of water is attached to each molecule of sodium carbonate. So let's get into the experiment. You're asked to measure out around about 5 grams. It's going to be hard to do that depending on how big your crystals are. So you'll take your actual value. So mine was around about 4.9 grams. And the volume of the volumetric flask that we diluted that into for my students was 250 centimeters cubed. And the volume of sodium carbonate pipetted into each flask, the volume of the base, is the usual figure of 25 centimeters cubed. So, volume of HCl, this has been standardized already by you in a previous experiment, so flick back to find your own molarity that you worked out. So the titration here, you can see that we've overshot in our first one, the rough titration, which was 22.5, but the second two was 21.4 and 21.5. So they're at a difference of 0.1, so we can use those titrations, get the average by adding them and dividing by 2, and we get 21.45 centimeters cubed. Now your average titration is probably going to be different than that, so use your average of the two closest titers that you have. The indicator used is methyl orange. So again, like the last titration, this is the equation that we're going to be working off. Our acid is HCl, our base is sodium carbonate. You see from the chemical equation, we're going to get Na and Nb. Na and Nb is the ratio of how many molecules or how many moles of sodium carbonate react with how many moles or molecules of HCl. So it's a 1 to 2 ratio. So that's where I'm getting Na is 2 and Nb is 1. So the base is 1, acid is 2. Just fill in your figures then, because this is going to be what we're using on the next page for our calculations. Your average titer, your molarity that you worked out previously in a separate experiment. This is from the equation. This is what you pipetted into the conical flask. This is what we need to find, the molarity of the sodium carbonate, so the concentration of it, so that we can work it out how many grams per litre are present and how many moles per litre, and the number is a 1. So here's my calculations with all those figures. Just put them in, put this into your calculator first, divide it by 25 then, and I got the molarity of the base to be 0.0429 moles per litre, or you can just write it as molar. Molar and moles per litre are the exact same thing. So next section, we're just going to fill this out. Number of moles of sodium carbonate in 1,000 centimeters cubed. That's the same as 1 litre. So these two figures should be the exact same. Number of moles in the volumetric flask. So in the volumetric flask, we didn't make it up to a litre. We made it up only to 250 centimeters cubed. So it's going to be a quarter of a litre. So if there's this amount of moles in a litre, we're going to divide it by 4, and that's going to be in 250 centimeters cubed, because there's 4 250s in a litre. So once we divide this number by 4, we'll get the number of moles in the actual volumetric flask. Now to switch that to grams per litre, we're going to come down here and we're just going to switch this to grams per litre. So here is my calculations for switching to the number of moles into 50 centimetres cubed. To get this value into grams per litre, we're going to use this equation. Number of moles equals mass over relative molecular mass. The relative molecular mass of the sodium carbonate is worked out over here. So 2 times 23 for sodium, plus 12 for carbon, plus 3/16 for the oxygen is 106. So this value is going to be different for you probably, depending on how many moles are in 250. This should be the same. Multiply them together and you'll get the amount of grams in 250 centimetres cubed. So you can put whatever value you get here up into this section. Now the original mass is whatever you weighed out. So I did 4.9 grams. The mass due to sodium carbonate, they should be the exact same result. Okay, so this value and this value should be the exact same. I just have 2 extra digits there. And then the mass due to water. So if we come down here, the mass due to water is written in here. Originally, we take the 4.9, which is how much solute we weighed out. This amount of grams is due to our sodium carbonate. That's what we figured out from the titration, that there was that much sodium carbonate present that reacted with our acid. If you take those away from each other, that leaves the rest of the substance that was in the solute, which has to be our water, crystallization. So this amount links to the mass due to water. So you're going to take this value away from the original mass. So this, take away this. And you're going to get 3.763.15 grams in my case. Definitely probably going to be different to yours. Percentage of water of crystallization then. To get a percentage, you're just going to compare the amount of water over the original amount of solute to see how much of that is within the 4.9. So you just put them over each other. You can see down here, 3.76315 over 4.9. So you're comparing the two results, multiplying it by 100 to get a percentage. And I got 76.79%. Again, it can be a completely different percentage to yours. It's just the method that you're looking at here. And that's going to go up into the percentage. The last part is to calculate the value of X in sodium carbonate times XH2O. So how many molecules of water are attached to each molecule of sodium carbonate? So I'm going to flip over and I'll show you how I did this. So in 250 centimetres cubed, we had 0.010725 moles of the sodium carbonate. This was we worked that out from the grams. So this was the amount of moles of water. So you can see 18. The mass of water that we had in the original amount of solute was 3.76315 for me. So I'm going to take mass divided by relative molecular mass and I'll get 0.209 moles of H2O in the 250 centimetres cubed as well. So in my original solute, in my original conical or volumetric flask of 250, I had this amount of moles of sodium carbonate, this amount of moles of water that were in the original 4.9 grams of solute that I had. So all of this is the water of crystallization. This is the sodium carbonate. All we need to do is just compare the two of them through a ratio. So here's the sodium carbonate, here's the water, divided by the smallest number. So I'm dividing by 0.010725, which is this number. That number divided by itself is going to be 1. This number divided by the smallest number is 19. So you can work out the ratio for each molecule of sodium carbonate. You're going to have 19 molecules of water Again, this is going to be different. In the exam questions, it's usually around 7 to 10, but it can go up to 15. That's just a general ball mark, so you know if you're kind of right. But this is what it ends up looking like for me.